Somewhere beneath the frozen silence of Antarctica, buried under miles of ancient ice, lies a quiet record of Earth's deepest memories. Not a book, not a monument, not a forgotten city, but layer upon layer of snow that slowly became ice, each one preserving a tiny piece of the atmosphere from a different age. Like pages in a diary, these frozen layers remember things that no human ever witnessed. They remember warm forests where ice now stands. They remember oceans that rose and fell. They remember animals that disappeared long before our first stories were ever told. And perhaps most mysterious of all, they remember a rhythm so slow that no single lifetime could ever notice it, a rhythm that returned again and again, almost every 100,000 years. Without warning, the world would slowly begin to cool. Winters became longer. Summers lost a little of their warmth. Snow that once melted completely began to survive through another season. Year after year, century after century, that snow quietly grew into enormous sheets of ice. Mountains disappeared beneath them. Rivers changed their course. Entire landscapes vanished beneath frozen silence. Then, after thousands of years, the ice would retreat once more. The forests returned. The rivers flowed again. Animals wandered back across lands that had once been impossible to cross. And eventually people followed. It happened not once, not twice, but over and over again. Almost as though our planet itself was breathing, slowly, patiently, beyond anything a human mind naturally understands. Tonight, we are going to follow that ancient rhythm, not to chase excitement, not to solve every mystery, but simply to walk beside one of the greatest natural stories ever written. Because the more quietly we listen to Earth's past, the more gently it begins to explain the world we live in today. And if these slow journeys into history help you discover wonders that are often hidden beneath everyday life, then perhaps this is exactly the kind of place worth returning to whenever you want your mind to slow down. Many people choose to stay connected with coding school for that reason. And if you find yourself enjoying this quiet exploration, you are always welcome to join them. And if this peaceful journey brings you a moment of calm, letting the video know through a simple like helps these stories continue reaching others who enjoy falling asleep while learning something extraordinary. Now, find a comfortable place. Allow your breathing to slow. There is no need to hurry anywhere tonight. The Earth certainly never has. For most of human history, people believed the world around them had always looked more or less the same. Mountains seemed permanent. Rivers appeared eternal. Forests looked timeless. It was easy to imagine that the planet had remained almost unchanged since the beginning. After all, our own lives are very short. A child grows into an adult. An old person remembers perhaps 80 or 90 years. A family might preserve stories stretching back a few generations. Ancient kingdoms sometimes recorded events that happened thousands of years earlier. But even the oldest civilizations could only remember a tiny moment compared with Earth's true history. Imagine watching a single second of a very long movie. Could you understand the entire story? Probably not. That is exactly how human history compares with the history of our planet. The Earth is around 4.5 billion years old. Modern humans have existed for only a very small fraction of that immense timeline. Everything we usually call history occupies only the final few moments. And during those final moments, something remarkable kept happening. The climate refused to stay the same. It shifted, sometimes slowly, sometimes almost unnoticed, but always with astonishing power. Long before anyone understood why, people living across different parts of the world noticed strange clues left behind by nature. Huge rocks rested in places where no nearby mountain could possibly have dropped them. Valleys looked as though giant invisible hands had carved them smooth. Long scratches covered solid bedrock. Lakes appeared in unusual shapes. Some hills looked almost sculpted. For centuries, nobody understood what had created these mysterious landscapes. Many explanations were offered. Some believed great floods had moved the rocks. Others imagined enormous earthquakes. Some even thought giants had wandered across the land. The truth turned out to be quieter, far quieter. Ice. Not the thin layer that forms on a winter morning. Not even the frozen surface of a familiar lake. But ice so vast that it could stretch across entire continents. Ice that moved, very slowly, almost too slowly to notice. Imagine standing beside a tree. If that tree grew 1 millimeter every day, you would never actually see it growing. Yet return after many years and it would be completely different. Glaciers behave in much the same way. Although they appear solid, enormous glaciers slowly flow under their own weight, not quickly enough for our eyes, but steadily enough to reshape the world. As these immense rivers of ice moved forward, they pushed rocks, crushed mountains, carved valleys, redirected rivers, and left behind countless clues that scientists still study today. For people living thousands of years ago, these clues must have seemed almost impossible to explain. How could such enormous stones appear hundreds of kilometers away from the nearest mountain? How could entire landscapes become polished smooth? How could valleys develop such graceful curves? Only much later did humans begin realizing that ice itself could become one of nature's greatest builders and greatest destroyers. Yet another quiet mystery remained. Why did these enormous glaciers appear at all? Why didn't Earth simply remain warm forever, or frozen forever? Why did it seem to move back and forth between different worlds? This question slowly attracted curious minds across Europe during the 18th and 19th centuries. At first, many scientists struggled to accept the idea. The thought that much of Europe had once been buried beneath kilometers of ice seemed almost unbelievable. Fields filled with crops, busy towns, ancient castles, all hidden beneath frozen sheets, it sounded impossible. Then evidence continued growing. Every expedition discovered new clues. Every valley seemed to tell the same story. The scratches matched, the rocks matched, the sediments matched. Little by little, an extraordinary picture emerged. Our planet had experienced immense ice ages. Not one, many. This realization quietly transformed how people understood Earth's history. Instead of imagining a stable planet interrupted only by occasional disasters, scientists began seeing something entirely different. They saw a living planet, a planet constantly changing, sometimes slowly enough that forests could adapt, sometimes quickly enough to reshape entire ecosystems. And perhaps most surprising of all, these changes appeared to follow certain patterns. Patterns hidden across enormous stretches of time. But discovering those patterns was far from easy. Imagine trying to understand the rhythm of ocean tides after watching the sea for only 10 seconds. You would probably think the water was standing still. Human civilizations faced exactly that problem. Even the longest kingdoms observed only a tiny fragment of Earth's climate story. No empire lasted long enough to witness an entire ice age begin. No written record survived long enough to watch one end. The clues had to come from somewhere else. Nature became the historian. Lake sediments quietly recorded changing seasons. Ocean floors accumulated microscopic shells. Caves slowly grew mineral layers. Trees added rings 1 year at a time. Corals built delicate skeletons beneath warm seas. Each archive preserved one small sentence of a story too large for any civilization to remember alone. When scientists learned to read these natural records, an astonishing picture slowly emerged. The climate had never stood completely still. Instead, it gently drifted between warmer and colder conditions, almost like breathing. Some changes lasted hundreds of years. Others stretched across thousands. Then researchers noticed something even more remarkable. The largest ice ages seemed separated by roughly 100,000 years. Not exactly. Nature rarely follows perfect calendars, but close enough that it demanded attention. Could Earth truly possess such a slow heartbeat? If so, what was keeping time? The answer did not seem to come from volcanoes alone, nor from the oceans, nor from changing continents. Instead, the search gradually lifted scientists' eyes towards something much farther away: the sun. Not because the sun itself changed dramatically, but because Earth never travels through space as simply as it appears. Most of us imagine our planet moving around the sun in a perfect circle. It feels natural, comforting, predictable. Reality is quieter and more beautiful. Earth's journey resembles a graceful dance. Sometimes its path becomes slightly more circular, sometimes a little more stretched. Sometimes its tilt changes almost imperceptibly. Sometimes the direction of that tilt slowly shifts like the wobble of a spinning top. Each movement is tiny, so tiny that no person notices it during a lifetime. Yet over tens of thousands of years, these subtle motions gently change how sunlight reaches different parts of our world. Imagine holding a small lamp over a globe. Move the lamp only a few centimeters. Tilt the globe just slightly. Nothing dramatic happens immediately. But keep making those tiny adjustments year after year for thousands of years, and eventually entirely different regions receive different amounts of light. Snow begins lasting a little longer. Ice reflects more sunlight. Cooler temperatures allow even more snow to survive. Little changes encourage larger ones. Nature begins responding. One season influences the next, then another, then another. What started as a tiny difference slowly grows into something capable of changing continents. This quiet chain reaction reminds us of something surprisingly familiar. A single snowflake weighs almost nothing. One snowfall rarely changes the world, but snowfall after snowfall, winter after winter, century after century, entire landscapes transform. Earth's great ice ages may have begun in much the same patient way, not through sudden catastrophe, but through countless small changes gently working together. That possibility raised another peaceful question. If tiny changes in sunlight could slowly guide ice ages, why did the strongest freezing seem to repeat close to 100,000 years instead of matching every orbital cycle exactly? Scientists would spend decades exploring that puzzle. Even today, it remains one of climate science's most fascinating mysteries, because nature rarely offers simple answers. Instead, it invites us to keep listening. Imagine standing on a quiet hillside nearly 1 million years ago. There are no roads, no cities, no distant lights glowing after sunset. The only sounds are the wind moving gently through scattered grasses, the calls of unfamiliar birds, and somewhere beyond the horizon, the slow rumble of water flowing through a valley that has not yet received a name. At first glance, the world appears peaceful. The air is cool but comfortable. Herds of ancient animals wander across wide open plains. Forests stretch for hundreds of kilometers without interruption. Rivers weave through the landscape exactly as they have for countless generations. Nothing suggests that this world is about to change. And yet, far to the north, a quiet transformation has already begun. Summer has become just a little weaker than before, not enough for anyone to notice during a single lifetime, perhaps not even enough for several generations to recognize. But somewhere high in the mountains, a small patch of winter snow refuses to melt completely. The following winter, another layer settles gently on top of it, then another, then another. No sudden storm announces the beginning of an ice age. No dramatic moment separates one world from the next. Instead, change arrives so slowly that every generation believes the landscape has always looked this way. Children grow into adults surrounded by almost the same forests their grandparents knew. Hunters continue following familiar animal paths. Birds still return each season. The rivers continue flowing. Everything feels permanent. Yet permanence is often only an illusion created by the shortness of our lives. If someone could return every 1,000 years to visit that same hillside, they would begin noticing something remarkable. The snowline has moved slightly lower. The summers have become just a little shorter. Small glaciers now cling to valleys where only bare rock existed before. Streams carry more crushed stone. Cold-loving plants quietly spread into regions that were once too warm for them. Still, life continues. Nature rarely rushes. Even enormous transformations often begin with almost invisible steps. This patient quality is one of Earth's greatest teachers. When we imagine change, we often picture explosions, earthquakes, storms, or volcanic eruptions. Those events certainly shape our planet, but some of Earth's greatest transformations happen without noise. They happen through repetition. A single drop of water seems harmless, yet millions of drops can carve a canyon. A single grain of sand appears insignificant, yet enough grains eventually build vast deserts. A single snowfall melts almost unnoticed, yet countless winters create glaciers that reshape continents. Earth seems to prefer this quiet method. Again and again, it reminds us that small changes repeated over immense periods become extraordinary. As the growing ice sheets expanded across northern lands, they began changing more than the temperature. They started changing the sky itself. Fresh snow reflects sunlight extremely well. Anyone who has walked outside after heavy snowfall knows how bright everything suddenly appears. Snow behaves almost like a giant mirror. Instead of absorbing much of the sun's warmth, it reflects a large part of that energy back into space. This creates an elegant feedback loop. More snow reflects more sunlight. More reflected sunlight means cooler temperatures. Cooler temperatures allow more snow to survive, which reflects even more sunlight. It is a cycle that gently strengthens itself. Scientists often describe this as one of Earth's natural feedback systems. The word feedback may sound technical, but the idea is surprisingly simple. Imagine placing a microphone too close to a speaker. A tiny sound becomes slightly louder. That louder sound is picked up again. It grows louder still. Soon the familiar high-pitched whistle fills the room. One small change reinforced itself. Nature contains many similar loops. Some calm the planet, others amplify change. Ice is one of the strongest amplifiers Earth possesses, yet even this was only one piece of a much larger puzzle, because while ice continued spreading, the oceans were quietly changing as well. When enormous amounts of water become locked inside glaciers, sea levels slowly fall, not by a few centimeters, but eventually by more than 100 meters. It is difficult to imagine such a change today. Picture standing on a modern beach. Now imagine the shoreline slowly moving farther away, not over one afternoon, not over 1 year, but over thousands of years. Generation after generation watches the sea retreat. New land gradually appears. Wide coastal plains emerge where fish once swam. River mouths move farther from the ocean. Entire islands become connected to continents. Places that today require ships could once be crossed on foot. One of the most famous examples is the land bridge that once connected Asia and North America. Today it lies beneath the cold waters of the Bering Strait. But during major ice ages, falling sea levels revealed a broad stretch of land. Not a narrow bridge in the way we usually imagine bridges. Rather, it was an enormous landscape filled with grasses, rivers, and animals. For countless generations, mammoths wandered there. Ancient bison grazed peacefully. Predators followed their herds. Eventually, small groups of humans also crossed this land, never realizing that future oceans would hide the path behind them. They were not setting out to discover a new continent. They were simply following food, following familiar landscapes, following life itself. To them, there was no dramatic crossing, no sign saying they had entered another part of the world, only open land stretching toward the horizon. The Ice Age quietly created one of the greatest migration routes in human history. Elsewhere, other land bridges appeared as well. Islands throughout Southeast Asia became connected in ways almost impossible to imagine today. Australia and New Guinea formed part of a much larger landmass known by scientists as Sahel. Although stretches of open water still remained, the distances between islands became much shorter than they are now. These changes influenced where people could travel, where animals could spread, and how entire ecosystems developed. The world map itself was constantly being redrawn, not by human hands, but by slowly advancing and retreating ice. If we could watch Earth from space over hundreds of thousands of years, coastlines would seem almost alive. They would slowly breathe, expanding, contracting, expanding once more. This image of breathing returns again and again whenever we study Earth's climate. Perhaps it is one of the most peaceful ways to imagine our planet, not frozen forever, not warm forever, but gently shifting between different states, always changing, always adapting. Long before modern science existed, people living close to nature probably noticed smaller versions of these rhythms. They watched rivers flood during certain seasons. They observed birds arriving and departing. They recognized cycles in the moon. Farmers learned when rains usually returned. Hunters understood when herds migrated. Human survival depended upon recognizing patterns. This ability became one of our species' greatest strengths. Our ancestors rarely possessed advanced technology, but they possessed careful observation. They noticed details because their lives depended upon them. A slight change in weather could determine whether crops survived. An unusual migration could mean food or hunger. Over thousands of years, humans became exceptional pattern seekers. Sometimes this ability served us wonderfully. Occasionally, it also led us to see patterns where none existed. Nature teaches both lessons. Some patterns are genuine, others only appear meaningful. The Great Ice Age cycle belongs firmly in the first category. Its fingerprints appear across oceans, caves, lakes, glaciers, and ancient sediments all around the world. Different scientists studying completely different environments repeatedly discovered the same broad rhythm. That agreement became one of the strongest pieces of evidence that Earth's climate truly followed long-term cycles. But discovering those cycles required remarkable patience. Unlike many scientific breakthroughs that happen through dramatic experiments, climate history was assembled like an enormous puzzle. One researcher might spend an entire career studying tiny shells resting on the ocean floor. Another devoted decades to measuring ice cores from Greenland. Someone else examined cave formations deep underground. Others analyzed pollen preserved inside ancient lakes. Each project seemed small by itself, yet together they formed something extraordinary. Imagine thousands of people scattered across the world, each holding one tiny fragment of a giant picture. No single person can understand the image alone. Only when every piece is carefully placed together does the full landscape emerge. Science often works exactly this way. Not through one brilliant discovery, but through many quiet discoveries patiently woven together. This approach feels surprisingly similar to nature itself. Small contributions repeated over time eventually create something magnificent. The same patience that built glaciers also builds understanding. As researchers continued collecting evidence throughout the 20th century, they gained increasingly detailed records of Earth's ancient climate. Some records stretched back hundreds of thousands of years. Others reached more than 1 million years into the past. Each new archive deepened the mystery. The 100,000-year rhythm appeared again and again, almost like the steady beat of an invisible drum. Still, another question quietly waited. If Earth's orbit changes gradually all the time, why does ice sometimes grow rapidly and sometimes remain surprisingly stable? Why do some cooling periods produce enormous continental glaciers while others pass more gently? The answer, scientists suspected, must involve more than sunlight alone. Earth behaves not like a single instrument but like a great orchestra. The sun provides one rhythm, the oceans add another. The atmosphere contributes its own gentle melodies. Mountain ranges influence winds. Sea ice changes reflection. Plants remove carbon from the air. Volcanoes occasionally introduce new ingredients. None performs alone. Each responds to the others. When their rhythms align in certain ways, remarkable changes become possible. Understanding this orchestra would become one of the greatest scientific journeys of the modern age. And perhaps the most fascinating part is that the music has never truly stopped. Even today, the same planet continues its slow dance through space, carrying us quietly along with it, just as it carried every generation that came before us. If we could gently step outside the flow of time and watch the Earth over several million years, something extraordinary would begin to appear. The continents would seem almost still. Mountain ranges would rise so slowly that they would look frozen in place. The oceans would quietly shift their shorelines. Forests would spread and retreat like soft green waves. And over everything else, The great ice sheets would slowly advance and withdraw again and again with remarkable patience. To a human observer living through only a few decades, the climate often feels unpredictable. One year is warmer, another is cooler. Some winters bring heavy snow while others seem unusually gentle. But viewed across hundreds of thousands of years, a hidden order begins to emerge. It is almost as though the Earth prefers balance. Whenever conditions drift too far in one direction, countless natural systems begin responding. Oceans absorb heat. Ice reflects sunlight. Forests capture carbon. Winds carry moisture across continents. Every part of the planet quietly communicates with every other part. No single force controls everything. Instead, millions of tiny processes work together continuously. This is one of the most beautiful lessons hidden inside Earth's history. Nature rarely depends upon only one answer. Instead, it creates harmony through countless connections. To understand this more clearly, let us travel beneath the surface of the sea. Far below the waves, where sunlight never reaches, the ocean floor appears calm and empty. Yet year after year, tiny organisms drift down from the surface after completing their brief lives. Many are so small they can barely be seen without a microscope. Some possess delicate shells made from calcium carbonate. Others build tiny skeletons from silica. After they settle onto the seabed, layer after layer slowly accumulates. One year adds only a paper-thin coating. 1,000 years create something thicker. 100,000 years produce an extraordinary archive. These sediments become one of nature's most reliable history books. Unlike human libraries, they never attempt to explain events. They simply preserve them. Each layer quietly records the conditions that existed when it formed. The temperature of the water, the chemistry of the ocean, sometimes even the amount of ice covering distant continents. For many years, these layers remained unnoticed. Ships crossed above them without realizing what rested beneath. Then, during the 20th century, scientists began collecting long cylinders of sediment from deep beneath the ocean floor. When they carefully examined these cores, they discovered something remarkable. Different layers contained slightly different forms of oxygen. At first, this sounded confusing. How could oxygen reveal ancient climates? The answer lies inside water itself. Every drop of water contains oxygen atoms. Most are a common form known as oxygen-16. A much smaller number belong to a heavier form called oxygen-18. Both behave almost the same. Almost. But during evaporation, the lighter oxygen-16 escapes into the atmosphere a little more easily. Snow forming over cold regions therefore contains relatively more oxygen-16. When enormous glaciers grow, they lock away tremendous amounts of this lighter water inside continental ice sheets. Meanwhile, the oceans become slightly richer in oxygen-18. Tiny marine organisms build their shells using whatever water surrounds them. Their shells quietly preserve this changing balance. Thousands of years later, scientists measure these tiny differences. The shells become silent thermometers, not because they contain temperatures directly, but because they preserve clues about how much ice existed across the planet when they formed. It is a wonderfully indirect method. Nature often hides its answers inside unexpected places. One small shell resting beneath several kilometers of ocean water can help describe the condition of ice sheets thousands of kilometers away. Little by little, these measurements produced one of the clearest climate records ever assembled. Warm periods appeared, cold periods followed, then warmth returned, again and again. The rhythm continued stretching back through time. Scientists gave these warm intervals a gentle name. They called them interglacials. An interglacial is simply a warmer chapter between major ice ages. Interestingly, we ourselves are living during one. Although modern discussions often focus on present-day climate changes, it is worth remembering that our entire civilization developed during an unusually warm and relatively stable interval. Agriculture expanded, cities appeared, writing emerged, large civilizations flourished. Most of recorded history unfolded during this calm chapter. Had the world remained locked beneath massive continental glaciers, human civilization would likely have developed very differently. Many fertile valleys would have remained buried beneath ice. Sea levels would have been much lower. Entire coastlines would have looked unfamiliar. Migration routes would have changed. The places where people settled would almost certainly have been different. In that sense, climate quietly shaped history long before history began recording itself. Most ancient civilizations never understood why certain lands were fertile. They simply accepted the landscapes they inherited. Few realized those landscapes had been prepared over countless thousands of years by retreating glaciers. As glaciers move, they grind enormous amounts of rock into fine particles. When the ice melts, these mineral-rich sediments spread across valleys and plains. Some of today's most productive farmland owes part of its richness to glaciers that disappeared thousands of years ago. The connection is almost poetic. The same ice that once made survival difficult eventually created conditions that supported agriculture. Nature rarely tells one-sided stories. What appears destructive in one age may become deeply beneficial in another. Consider the Great Lakes of North America. Today they contain nearly 1/5 of the world's fresh surface water. Millions of people live nearby. Ships travel across them. Entire economies depend upon them. Yet these vast lakes exist largely because ancient glaciers slowly carved enormous basins into the land. As the ice finally retreated, meltwater filled those basins. Without the Ice Age, the Great Lakes as we know them might never have existed. Northern Europe tells a similar story. Many of its beautiful lakes, rolling hills and smooth valleys were carefully shaped by glaciers advancing and retreating over immense spans of time. The landscapes tourists admire today often owe their appearance to events that unfolded tens of thousands of years before the first villages were built. Scotland's dramatic glens, Norway's magnificent fjords, the countless lakes of Finland, large parts of Canada, each quietly remembers the movement of ice. Sometimes those memories appear as polished rock surfaces. Sometimes as winding ridges of gravel left behind by melting glaciers. Sometimes as enormous boulders resting far from the mountains where they originally formed. Every landscape carries its own memory. Learning to recognize these memories changes the way we see the world. A quiet valley is no longer simply beautiful. It becomes a chapter of Earth's autobiography. A lonely boulder becomes a traveler from another place. A smooth hillside becomes evidence of unimaginable patience. Perhaps this is one reason geology feels so calming. It gently reminds us that the planet has never hurried. Everything we consider ancient often belongs only to the final pages of a much longer story. While glaciers shape the land, they also influence the lives of countless animals. During colder periods, species gradually shifted toward warmer regions. Some adapted remarkably well. The woolly mammoth developed thick, insulating fur and a layer of fat beneath its skin. Its small ears helped reduce heat loss. Its curved tusks may have assisted in clearing snow while searching for food. Nearby wandered the woolly rhinoceros, another impressive survivor of cold grasslands. Reindeer migrated across vast frozen plains. Musk oxen gathered together against bitter winds. Large predators followed these herds. Among them were cave lions, wolves, and saber-toothed cats in some regions. Despite the harsh conditions, these ecosystems supported extraordinary diversity. An Ice Age landscape was not an endless frozen desert. Much of it consisted of broad grasslands known today as the Mammoth Steppe. These plains stretched across enormous distances. Rich grasses supported huge grazing animals. Where herbivores gathered, predators naturally followed. It was a living world full of movement. Humans eventually entered this landscape as well. Our ancestors did not conquer the Ice Age through strength alone. Compared with mammoths, they were physically small. Compared with cave bears, they were vulnerable. Compared with wolves, they lacked sharp teeth. Their greatest advantage lay elsewhere: cooperation, communication, curiosity, adaptability. They learned to make clothing from animal hides. They built shelters. They mastered fire. They shared knowledge between generations. Every new idea became part of a growing library carried not in books, but in memory. Unlike many animals, humans could solve new problems without waiting for evolution to reshape their bodies. They reshaped their behavior instead. This flexibility became one of our species' greatest strengths. Whenever climates changed, people adjusted. They moved, they experimented, they observed, and perhaps most importantly, they remembered. Each generation inherited lessons gathered by those before it. Over time, those accumulated observations became culture itself. The Ice Age did not simply challenge humanity. In many ways, it quietly trained us. It encouraged planning, cooperation, innovation, patience, qualities that would later support farming, villages, trade, and civilization. Without realizing it, our ancestors were being shaped not only by nature, but by the slow rhythm of time itself. When we think about the Ice Age, it is easy to imagine a world covered entirely by snow and endless frozen wilderness. The image is familiar: towering walls of ice, blinding white landscapes, bitter winds that never stop blowing. Although scenes like these certainly existed, they tell only part of the story. The real Ice Age was far more varied. Some regions were buried beneath ice several kilometers thick. Others remained surprisingly green. Some valleys supported forests. Others became wide grasslands stretching farther than the eye could see. The earth did not simply become frozen. It became different. This difference is important because life rarely disappears all at once. Instead, it moves. Plants slowly spread toward places where conditions become more favorable. Animals quietly follow the plants. Predators follow the animals. Humans, in turn, follow opportunities wherever they appear. Seen this way, the history of climate is also the history of movement. Every major change in temperature gently encouraged millions of living creatures to begin walking in new directions. Sometimes those journeys lasted only a few generations. Sometimes they continued for thousands of years. Imagine standing on a high ridge somewhere in Central Europe 40,000 years ago. To the north, enormous glaciers shimmer beneath pale sunlight. To the south, rolling plains stretch toward distant mountains. Herds of horses graze peacefully. Reindeer move steadily across open country. Small bands of humans travel quietly through the landscape. They leave almost nothing behind except footprints that disappear with the next snowfall. Unlike modern travelers carrying maps, they possess something even more valuable: careful observation. They know where fresh water can be found. They recognize which valleys remain sheltered from harsh winter winds. They understand which plants become edible during different seasons. They know when animals migrate. Their knowledge does not come from books. It comes from listening. Listening to birds, listening to rivers, listening to changing skies, listening to generations of experience carefully shared around evening fires. The Ice Age demanded attention. Anyone who ignored nature's signals risked making dangerous decisions. This constant observation gradually shaped the human mind. Even today, many of us instinctively notice changing weather without consciously trying. We glance at clouds before rain. We sense seasonal shifts through temperature and daylight. Perhaps these quiet habits are distant echoes from lives lived under much greater environmental uncertainty. For our ancestors, weather was never a casual conversation. It influenced every decision. A warmer spring meant earlier plant growth. A colder autumn required quicker preparation. A delayed migration could change hunting plans entirely. Everything depended upon paying attention. As thousands of years passed, humans spread into environments unlike anything their earliest ancestors had known. Some groups learned to survive close to advancing glaciers. Others settled near rivers formed by seasonal meltwater. Some occupied sheltered caves overlooking open plains. Each region taught different lessons. Each landscape encouraged different solutions. This diversity of experience quietly expanded humanity's collective knowledge. No single group understood everything. Together, however, human communities accumulated an astonishing understanding of nature. Long before science existed as we know it today, people had already become skilled observers of changing climates. They noticed which stars appeared during certain seasons. They recognized recurring animal migrations. They understood how snow behaved in different valleys. Although they lacked modern explanations, they possessed practical wisdom gained through direct experience. This reminds us that knowledge takes many forms. Scientific instruments measure the world with extraordinary precision. Traditional experience often notices patterns that emerge through long familiarity. Both approaches begin with the same simple act: observation. Perhaps that is why curiosity has always been one of humanity's greatest gifts. Long before telescopes, satellites, or computers, someone first wondered why rivers flooded. Someone else asked why certain birds disappeared every winter. Another person noticed that particular plants always bloomed after certain rains. Civilization itself may have begun with quiet questions. The same spirit continues today. Modern scientists still begin by noticing something unusual. Then comes patience, measurements, careful comparisons, slow understanding. In many ways, the scientific method reflects the pace of nature itself. Nothing is rushed. Evidence accumulates gradually. Conclusions remain open to improvement whenever new information appears. This patient approach became especially important while studying ancient climates. Unlike many branches of science, climate research rarely depends upon a single discovery. Instead, it resembles assembling an enormous mosaic. One laboratory studies pollen trapped inside ancient lake sediments. Another analyzes tiny air bubbles preserved deep within Antarctic ice. A third measures minerals inside cave formations. Elsewhere, researchers examine fossil corals, volcanic ash, tree rings, peat bogs, and desert dunes. At first, these subjects seem unrelated, yet everyone preserves part of the same story. The beauty of this approach lies in confirmation. If many completely different natural archives independently tell similar stories, confidence gradually grows. Imagine asking 100 people to describe the same sunrise from different hillsides. Each description would differ slightly. One person notices birds, another remembers colors, someone else describes morning mist. No account is identical, yet together they reveal the same sunrise. Nature works similarly. Each archive emphasizes different details. Together they reveal Earth's changing climate. Among the most remarkable archives ever discovered are the great ice cores drilled from Greenland and Antarctica. These cylinders of ice appear surprisingly ordinary at first glance, transparent, cold, silent. Yet they contain one of the greatest historical collections ever assembled. Each year, fresh snowfall gently covers the previous year's surface. Over time, new snow compresses older layers beneath it. Eventually, the lower snow transforms into solid ice. The process is slow, patient, almost impossible to notice in everyday life. But over hundreds of thousands of years, these annual layers build an extraordinary vertical timeline. Scientists carefully drill through them using specialized equipment. The resulting ice core resembles a frozen history book stretching deep beneath the surface. Some cores preserve climate records extending back more than 800,000 years. That number is difficult to imagine. 800,000 years, long before pyramids, long before agriculture, long before written language, long before modern humans spread across most of the world. Yet the ice remembers. Tiny bubbles trapped inside each layer preserve samples of ancient air. Not a reconstruction, not an estimate. Actual air breathed by animals and carried through ancient forests hundreds of thousands of years ago. Opening one of these bubbles is like quietly uncorking a message from another age. Scientists measure the gases trapped inside with astonishing precision. Carbon dioxide, methane, other atmospheric components. Together they reveal how Earth's atmosphere changed through time. Again, another remarkable pattern appeared. During colder periods, carbon dioxide levels generally became lower. During warmer intervals, they increased. This relationship fascinated researchers. Was carbon dioxide driving climate changes? Was climate altering carbon dioxide? Or were both influencing each other simultaneously? The answer proved beautifully complex. Earth rarely follows simple one-way relationships. Instead, countless feedback loops operate together. Warmer oceans release certain gases. Colder oceans absorb more. Growing forests remove carbon from the atmosphere. Changing temperatures influence vegetation. Vegetation influences soil. Soil affects atmospheric chemistry. The atmosphere influences temperature. Temperature changes the oceans. The oceans influence ice. The ice changes sunlight reflection. Every part responds to every other part. The climate behaves less like a machine and more like a living conversation. No single voice dominates. Instead, countless natural systems continuously exchange information. Perhaps this explains why predicting climate has always remained challenging. Even small changes can ripple through many connected systems. The ancient ice teaches another gentle lesson. Everything is connected. A snowstorm falling in one region may eventually influence rivers hundreds of kilometers away. Ocean currents affect rainfall on distant continents. Mountain ranges redirect winds. Plants shape the atmosphere that supports animals. Humans become part of this web as well. We often imagine ourselves standing outside nature. History suggests otherwise. Every civilization has depended upon stable seasons, reliable water, healthy soils, predictable harvests. Even the greatest empires quietly rested upon environmental foundations built over thousands of years. When those foundations shifted, societies often adapted, sometimes successfully, sometimes with great difficulty. Long before kings, philosophers, merchants, or explorers appeared, the slow rhythm of Earth's climate had already begun preparing the stage upon which human history would unfold. The more deeply we explore the Ice Age, the more it seems less like a distant geological event, and more like a silent architect whose work still surrounds us today. There is something surprisingly comforting about realizing that the Earth has never been completely still, not because change is always easy, but because change is natural. The mountains we admire today were once hidden beneath ancient seas. The deserts we now associate with endless dryness were, at different times in Earth's history, filled with rivers, lakes, and green grasslands. Even the mighty Sahara, now stretching across northern Africa, has not always been a desert. Thousands of years ago, during warmer and wetter periods, much of that vast region looked completely different. Lakes reflected the sky. Hippos wandered through slow-moving rivers. Fish swam where endless dunes now rise. People painted giraffes, elephants, and crocodiles onto cave walls because those animals truly lived there. Today those paintings remain, quietly reminding us that landscapes are temporary visitors in Earth's much longer story. The Ice Age teaches this lesson repeatedly. Nothing remains exactly the same forever. The glaciers advanced, then they retreated. Forests disappeared, then returned. Grasslands spread, then slowly gave way to trees once more. Animals migrated. Some adapted, some disappeared, others evolved into new forms. Every change became the beginning of another chapter. This rhythm shaped not only landscapes but also the opportunities available to our ancestors. Imagine a family living near the edge of a great glacier. For generations they have followed herds across open grasslands. Their children learn familiar paths through valleys and rivers. Life feels predictable. Then, almost without anyone noticing, the climate begins warming. Not over days, not over years, but over centuries. The ice slowly withdraws. The rivers become larger with seasonal meltwater. Young forests begin appearing where open plains once stretched. The familiar routes followed by animals gradually change. Some species move north. Others disappear from the region altogether. The people adapt. Perhaps they begin fishing more often. Perhaps they hunt different animals. Perhaps they discover new plants becoming available each spring. None of these adjustments happen suddenly. Every generation simply hands slightly different knowledge to the next. Over enough time, an entirely new way of life quietly develops. This slow transformation explains something important about human history. Great changes rarely arrive as dramatic moments experienced by everyone at once. Most are built from countless tiny decisions made by ordinary people responding to changing conditions. History often remembers kings. Nature remembers everyone. Every family searching for fresh water. Every hunter choosing a different route. Every child learning where berries now grow. Each small decision became part of humanity's larger journey. In this way, climate never forced history down a single path. Instead, it gently shaped the choices available. It opened some roads while quietly closing others. A river changed direction. A coastline moved farther away. A valley became fertile. A mountain pass remained blocked by ice for thousands of years. People responded to these changing opportunities with remarkable creativity. Perhaps no quality defines humanity better than adaptability. Unlike many animals, humans rarely depended upon one environment alone. We learned to survive in forests, deserts, mountains, coastlines, grasslands, frozen tundra, and tropical islands. Each place required different skills, different tools, different traditions, yet all belonged to the same species. The Ice Age became an extraordinary teacher. It rewarded flexibility. Groups able to observe carefully and adjust gradually often survived changing conditions more successfully than those relying only upon familiar routines. This lesson continues throughout history. Agriculture required adaptation. Cities required adaptation. Ocean travel required adaptation. Industrial technology required adaptation. Every generation has inherited a world slightly different from the one known by its grandparents. Perhaps this is simply Earth's oldest tradition, change. But while humans were learning to adapt, another remarkable system continued operating quietly beneath the surface of the oceans. Ocean currents. Most of us have looked at maps showing continents separated by blue water. The oceans appear calm and still. In reality, they are constantly moving. Invisible rivers flow through them. Some carry warm tropical water toward colder regions. Others transport cold water back toward the equator. Together they form one of Earth's greatest circulation systems. Imagine placing a pot of water over gentle heat. As the lower water warms, it rises. Cooler water sinks. Slow circulation begins naturally. The oceans behave similarly, although on a scale almost impossible to imagine. Temperature differences, salt content, wind patterns, Earth's rotation, all help move water around the globe. This circulation quietly redistributes heat between different regions. Without it, many places would experience far more extreme climates. Western Europe, for example, enjoys milder winters partly because warm ocean currents carry heat across the Atlantic. If those currents behaved differently, entire regions might experience very different weather. Scientists studying ancient climates realized that these currents also changed during major ice ages. As glaciers expanded, fresh water from melting ice sometimes entered the oceans in enormous quantities. Fresh water is lighter than salty seawater. When enough entered certain regions, it altered the normal sinking and rising of ocean water. This, in turn, influenced ocean circulation itself. One quiet change triggered another, then another. The climate responded through a complex web of interactions. Again, we see the same lesson. Nothing exists alone. Ice influences oceans. Oceans influence atmosphere. Atmosphere influences rainfall. Rainfall influences forests. Forests influence carbon. Carbon influences temperature. Temperature influences ice once again. The cycle continues. Nature prefers relationships over isolation. Perhaps this idea feels familiar because human societies work in much the same way. Farmers depend upon rivers. Cities depend upon farmers. Merchants connect distant communities. Teachers preserve knowledge. Families support one another across generations. Everything flourishes through connection. The Earth has quietly followed this principle for billions of years. As researchers continued uncovering evidence from around the world, another fascinating realization slowly emerged. Not every ice age looked exactly the same. Some were longer, some shorter, some produced larger glaciers, others remained relatively modest. The famous 100,000-year rhythm was real, yet every cycle possessed its own unique personality. This is another reason scientists remain fascinated today. Nature follows patterns, but it rarely repeats itself perfectly. Think about the seasons. Every spring brings new leaves. Every autumn brings falling ones. Yet no two springs are completely identical. Some begin earlier, others are cooler. Rainfall differs. Flowers bloom at slightly different times. The pattern remains. The details vary. Earth's long climate cycles behave similarly. Each follows familiar rhythms while creating entirely new combinations of conditions. This flexibility makes our planet remarkably resilient. Instead of becoming locked permanently into one climate, it continually adjusts. Sometimes the changes unfold almost invisibly. Sometimes they become large enough to reshape continents. And throughout it all, life continues finding new ways to survive. This persistence is perhaps one of the most inspiring themes in Earth's history. Again and again, environments changed. Again and again, life responded. Plants spread into newly available landscapes. Animals migrated toward favorable climates. Humans learned, adapted, remembered, and passed their knowledge forward. The Ice Age was never simply a story about cold. It was a story about resilience, a story about patience, a story about quiet transformation unfolding over timescales almost beyond imagination. Yet one question still remained. If scientists had discovered evidence for repeating ice ages, if they had identified changes in Earth's orbit, if they had uncovered records preserved in ice, oceans, caves, and lakes, why did the strongest glacial cycles become so dominant only during the more recent part of Earth's history? Why did the rhythm itself seem to change? That quiet mystery would eventually lead researchers even deeper into the planet's past, toward a chapter of Earth's history far older than humanity itself, where the foundations of the modern climate system were first beginning to take shape. To understand why the great 100,000-year rhythm became so powerful, we must travel much farther back than the first humans, far beyond the mammoths, far beyond the earliest stone tools, far beyond anything that resembles the modern world. The journey takes us several million years into the past, to a time when the Earth looked familiar in some ways and completely different in others. The continents already occupied positions close to where we recognize them today. The Atlantic Ocean separated Europe and North America. Africa had already drifted northward. Australia stood apart in the southern hemisphere. Yet the climate told another story. Many regions were warmer than they are now. Forests stretched across lands that today experience long winters. Sea levels stood higher. The great northern ice sheets that would later dominate so much of the planet had not yet fully developed. The Earth was certainly changing, but not in the dramatic rhythm that later became so familiar. Scientists call this period the Pliocene epoch, a chapter that lasted from about 5.3 million to 2.6 million years ago. It was, in many ways, a world standing quietly between two different ages. One foot remained in a warmer past. The other was slowly stepping toward the colder planet we know today. Nothing dramatic announced this transition. Instead, the Earth began making countless tiny adjustments. One of the most important involved the atmosphere itself. For millions of years, volcanic eruptions, weathering of rocks, plant life, and oceans had all been quietly exchanging carbon dioxide. Sometimes more entered the atmosphere, sometimes less. Gradually, over immense spans of time, atmospheric carbon dioxide slowly declined compared with much earlier periods in Earth's history. The change was not sudden. Imagine lowering the brightness of a lamp by only the smallest amount each year. You would never notice the difference from one evening to the next. Yet after thousands of adjustments, the room would become noticeably dimmer. Earth's atmosphere experienced something similar. The overall warming influence slowly weakened, not enough to transform the planet overnight, but enough to make long-lasting ice increasingly possible. At almost the same time, another enormous event had already begun reshaping global climate. Several million years earlier, North America and South America had become connected by the narrow strip of land we know today as the Isthmus of Panama. Before that connection formed, seawater moved freely between the Atlantic and Pacific Oceans. When the land bridge gradually rose, those waters could no longer mix so easily. Ocean circulation changed. Currents that had wandered freely now followed different routes. Some researchers believe this strengthened the warm current flowing across the North Atlantic. More moisture reached northern regions. Greater snowfall became possible. If winters remained cold enough, more snow survived each summer. Again, tiny changes quietly reinforced one another. None of these events alone created the great ice ages, but together they prepared the stage. Nature rarely depends upon one cause. Instead, many gentle influences gradually combine until a threshold is crossed. Imagine filling a large bowl with water. Each drop seems unimportant. One more drop changes almost nothing. Another appears equally insignificant. Eventually, however, one final drop causes the bowl to overflow. People often notice only the last drop. Nature remembers every one that came before. The great ice ages likely emerged through countless small contributions working together across millions of years. As conditions slowly cooled, permanent ice began expanding in the northern hemisphere. At first, these glaciers remained relatively modest. Then, little by little, they became larger. With each major advance, the landscape changed more dramatically. Rivers adjusted, forests shifted, sea levels responded, animals migrated. Human ancestors, still living mostly in Africa, continued evolving within a world becoming increasingly variable. This changing environment may have influenced human evolution in subtle ways. Scientists continue discussing exactly how much. No single answer satisfies every question, but many researchers agree on one idea. Living in a world where environments changed repeatedly encouraged flexibility. Instead of adapting to one perfectly stable habitat, our ancestors faced shifting conditions. Grasslands expanded, woodlands returned, rainfall varied, food sources changed. Those capable of adjusting to new circumstances often gained an advantage. Over hundreds of thousands of years, this flexibility became deeply woven into human behavior. Perhaps one reason humans eventually spread across nearly every environment on Earth is that our ancestors had already learned how to cope with change itself. The climate became an instructor, not through intention, simply through repetition. Every generation encountered slightly different conditions. Every generation learned. Every generation passed those lessons onward. This slow accumulation of experience shaped not only survival but also curiosity. People who observe carefully tend to ask questions. Why have the rains changed? Why do certain animals arrive later than before? Why has the river become smaller? Such questions lie at the heart of science, even if the earliest observers possessed no formal scientific language. Curiosity did not begin in laboratories. It began around campfires. It began during long walks across open landscapes. It began whenever someone quietly wondered why the world behaved as it did. Thousands of generations later, modern scientists continue asking remarkably similar questions. Only the tools have changed. Instead of footprints, they examine satellite images. Instead of guessing from river levels alone, they measure ancient isotopes trapped inside ice. Instead of relying solely upon memory, they use computers capable of processing enormous amounts of information. Yet the central question remains wonderfully familiar. Why? Why does the Earth change? Why does the climate follow these rhythms? Why did one pattern become stronger than another? One powerful tool helping answer these questions is something known as a climate model. Despite the name, a climate model is not a miniature Earth sitting inside a laboratory. It is a mathematical representation of how different parts of the climate system interact. Scientists carefully describe known physical processes, how sunlight warms the surface, how air moves, how water evaporates, how clouds influence temperature, how oceans transport heat. Then computers calculate how these processes influence one another over long periods. The results do not provide perfect predictions. Nature is far too complex for complete certainty. Instead, models allow researchers to test ideas. What happens if Earth's orbit changes? What if carbon dioxide becomes lower? How does expanding sea ice influence temperature? What role do ocean currents play? Each experiment helps scientists compare computer results with evidence preserved in natural archives. If both tell similar stories, confidence gradually grows. This method resembles solving a historical mystery. Imagine discovering footprints, old letters, and forgotten maps describing the same journey. None alone proves everything. Together they build a convincing picture. Climate science follows that same patient philosophy. Evidence from many independent sources gradually converges. Perhaps this is one reason the field inspires such respect among researchers. It requires extraordinary patience. A scientist may spend years studying one tiny part of an immense system. Another dedicates decades to understanding ocean circulation. Someone else investigates clouds. Another focuses on ancient pollen. Individually, their work appears narrow. Collectively, it becomes astonishingly broad. This cooperation reflects another quiet lesson from nature. Just as ecosystems depend upon countless interacting species, understanding the Earth depends upon countless interacting minds. No one person solves the puzzle alone. Knowledge grows through collaboration, generation after generation, exactly as human culture has always grown. And even after more than a century of research, one aspect of the Ice Age story continues to fascinate scientists more than almost any other. The 100,000-year rhythm is real. The evidence supporting it is overwhelming. Yet understanding precisely why that rhythm became so dominant remains one of the great scientific conversations of our time. Some researchers emphasize the growth and collapse of massive ice sheets. Others focus on interactions between the oceans and atmosphere. Still others examine carbon dioxide, dust, sea ice, or subtle changes in Earth's orbit working together. Perhaps the most honest answer is also the most beautiful one. The Earth does not tell simple stories. It tells interconnected ones. Every glacier, every ocean current, every forest, every cloud, every mountain range, and every ray of sunlight contributes a quiet sentence to the same remarkable story. A story that has been unfolding patiently for millions of years, long before the first human ever looked up at the stars and wondered how the world came to be. For a long time, one idea seemed almost impossible to accept. How could tiny changes in Earth's movement around the sun eventually lead to ice sheets that covered millions of square kilometers? The difference in sunlight caused by these orbital changes is surprisingly small. If we could somehow stand outside our planet and measure the amount of energy reaching Earth during these slow cycles, we would not see enormous swings. The sun itself does not suddenly become dramatically brighter or dimmer every 100,000 years. Instead, the changes are subtle, almost delicate. And yet, those delicate changes somehow guide some of the largest climate shifts our planet has ever experienced. This quiet contradiction puzzled scientists for decades. Many compared it to pushing a child on a swing. A single gentle push does not move the swing very far, but if each push arrives at exactly the right moment, the movement slowly grows larger. The strength of each push matters less than its timing. Earth's orbit appears to work in a surprisingly similar way. Its slow changes gently influence where and when sunlight reaches different parts of the world. The timing of those changes becomes incredibly important. One place deserves special attention: the far north, especially the regions surrounding the Arctic Circle. At first, this may seem strange. After all, the tropics receive much more sunlight overall. Why should the Arctic matter so much? The answer lies in summer, not winter. Winter is always cold enough for snow to fall across much of the far north. But winter alone does not build glaciers. Summer decides their future. Imagine two different years. During the first year, heavy snow falls throughout winter. Then a warm summer arrives. Almost every snowflake melts away. When autumn returns, the landscape begins again from the beginning. Now imagine a second year. Winter brings the same snowfall, but summer is slightly cooler. Only a small amount of snow survives. The following winter adds another fresh layer. Next summer melts part of it, but not all. Another winter arrives. More snow accumulates. Very slowly, the remaining snow becomes compressed. Loose snow turns into firn, a dense, grainy material that lies somewhere between snow and solid ice. Over many years, firn becomes glacier ice. Everything depends upon one simple question. Does a little snow survive the summer? If the answer remains yes for centuries, glaciers begin growing almost naturally. This is why scientists pay such close attention to northern summers. Tiny differences in summer sunlight can quietly determine whether ice slowly expands or gradually disappears. The remarkable part is that Earth possesses several different orbital rhythms working together at the same time. One rhythm changes the shape of Earth's path around the Sun. Sometimes that path becomes slightly more circular, sometimes slightly more stretched. This cycle unfolds over roughly 100,000 years. Another rhythm changes Earth's tilt. Today our planet leans by about 23.5 degrees. That tilt is never perfectly constant. Over many thousands of years, it gently increases and decreases. A larger tilt creates stronger seasons, hotter summers, colder winters. A smaller tilt softens those seasonal differences. Then there is another graceful movement. Earth slowly wobbles as it spins, much like a spinning top beginning to shift direction. This wobble changes which season occurs when Earth is closest to the Sun. Again, the change is incredibly slow, far too slow for anyone to notice within a lifetime. Individually, none of these rhythms explains everything. Together, however, they begin composing an elegant celestial dance. The Serbian mathematician and engineer Milutin Milankovic devoted years of careful work to understanding these orbital variations. Working during the early 20th century, long before powerful computers existed, he patiently calculated how Earth's changing orbit could influence the distribution of sunlight over immense periods of time. His calculations required extraordinary persistence, page after page of mathematics, careful astronomical observations, years of thoughtful analysis. Milankovic believed these slow orbital changes could help explain the great ice ages. At the time, many people remained uncertain. The evidence simply was not complete enough. Only decades later, when scientists recovered longer climate records from deep-sea sediments and polar ice, something remarkable happened. The predicted orbital rhythms began appearing inside the geological evidence itself. It was one of those rare moments when independent discoveries quietly met one another across time. Astronomers studying planetary motion, and geologists studying ancient sediments had unknowingly been reading different chapters of the same story. Yet another mystery remained. If the 100,000-year orbital cycle changes sunlight only modestly, why does the climate respond so strongly? Researchers gradually realized that Earth's climate behaves much like a carefully balanced set of scales. A very small influence can produce a much larger result if several natural feedback systems begin reinforcing one another. Consider a simple example. Imagine lighting a small candle inside a dark room. The candle itself produces only a modest amount of light, but if that light allows you to find a lantern, and the lantern helps you light several more, the final brightness becomes far greater than the original flame alone. The first change begins the process. The later changes strengthen it. Earth's climate appears to operate in a similar fashion. Orbital changes provide the initial gentle push. Ice begins expanding. Expanding ice reflects more sunlight. Cooler temperatures allow additional snow to survive. Growing glaciers influence wind patterns. Ocean circulation gradually adjusts. Vegetation changes. Carbon dioxide levels slowly respond. Each process quietly strengthens the next. The result becomes much larger than the original orbital change by itself. This helps explain why nature often appears surprisingly sensitive, not because one tiny influence possesses enormous power alone, but because many connected systems respond together. The atmosphere, oceans, ice sheets, forests, soils, clouds, and sunlight all participate in one continuous conversation. Listening to only one voice can never reveal the whole discussion. Perhaps this is why climate science feels less like solving a simple equation and more like understanding an orchestra. A violin alone cannot perform an entire symphony. Neither can a single drum. Every instrument contributes. Sometimes one leads. Sometimes another becomes more important. The beauty comes from their interaction. Earth's climate has performed that quiet symphony for millions of years. As researchers continued improving their understanding, another fascinating discovery slowly emerged. The great ice sheets themselves possess remarkable patience. Unlike storms, they do not respond immediately. Imagine placing a large block of ice beneath the morning sun. It does not vanish instantly. Even after several hours, much of it remains. Now imagine an ice sheet several kilometers thick covering an area larger than many countries combined. Its response becomes even slower. Ice remembers. It carries the influence of previous centuries into the future. Even if summers become slightly warmer, enormous glaciers require thousands of years to fully respond. Likewise, once they begin growing, they continue expanding long after the original conditions first encouraged them. Scientists sometimes describe this as the climate system having a long memory. That memory is one reason the great glacial cycles unfold so gradually. The Earth does not rush from one state to another. It eases into change, century after century, millennium after millennium. The planet seems almost to pause, carefully considering each step before taking the next. There is something deeply calming about that image. A world that transforms not through haste but through patience. A reminder that some of the greatest changes in history were never loud enough for anyone living at the time to notice. They simply became visible when countless quiet moments were added together, one after another, across the immeasurable passage of time. As our quiet journey slowly comes to an end, we return to the same question that first invited us into this story. Why did the Earth enter a deep freeze every 100,000 years? Perhaps the most honest answer is also the most beautiful one. Not because of one single force, not because of one dramatic event, but because countless gentle processes work together with extraordinary patience. The Earth's orbit slowly changed. Its tilt shifted almost imperceptibly. Its path around the sun became slightly more circular, then slightly more stretched. Summer sunlight in the far north gently increased, then gently decreased. Snow survived a little longer. Ice reflected more sunlight. The oceans quietly adjusted their currents. The atmosphere responded. Forests expanded and retreated. Carbon dioxide rose and fell. Each change encouraged another. Like musicians performing different melodies, every part of the planet contributed to a single, magnificent symphony that unfolded over hundreds of thousands of years. No human civilization witnessed an entire ice age begin. No king watched a glacier advance across a continent. No ancient storyteller lived long enough to describe the complete rhythm. And yet the evidence remained patiently waiting. It waited inside mountain valleys. It rested beneath the ocean floor. It slept inside cave formations. It remained locked within tiny bubbles of air trapped deep inside Antarctic ice. Generation after generation, the Earth quietly preserved its own memories until curious minds finally learned how to read them. Perhaps that is one of the most inspiring parts of this story. The planet never hid its history. It simply wrote it in a language that took humanity thousands of years to understand. The scratches on ancient rocks, the lonely boulders carried far from their birthplace, the shells resting beneath the sea, the rings inside old trees, the layers of snow that slowly became ice. Every one of them whispered the same message. The world has always been changing, slowly, patiently, beautifully. For early humans, these great climate cycles shaped nearly every chapter of survival. They influenced where people walked, where animals gathered, where rivers flowed, and where fertile land eventually appeared. Without those slow changes, the paths our ancestors followed might have been completely different. The places where villages grew, the valleys where farming began, the coastlines where great civilizations later flourished. All were quietly influenced by decisions made not by people, but by nature itself over immense stretches of time. History is often written as the story of emperors, explorers, inventions, and battles. Yet beneath every human achievement lies another history, the history of the Earth, a history that began billions of years before the first words were spoken, a history that continues even now. Sometimes we imagine ourselves standing apart from nature. The story of the ice ages reminds us otherwise. We breathe the same atmosphere. We drink water that has traveled through countless ancient rivers, glaciers, clouds, and oceans. We walk across landscapes shaped by ice that vanished thousands of years before our ancestors arrived. The ground beneath our feet remembers a past far older than any nation. Even today, Earth's slow dance through space continues. The planet still circles the sun. Its axis still tilts. Its orbit still changes, just as it has for millions of years. The great celestial rhythm has never stopped. We simply experience only the briefest heartbeat of that endless cycle. Perhaps there is something comforting in that thought. Our own lives often feel busy. Days seem full. Years pass quickly. Yet beyond our schedules and calendars, the Earth continues moving with remarkable patience. Mountains weather grain by grain. Forests grow leaf by leaf. Rivers carve valleys drop by drop. Glaciers, when they exist, move almost too slowly for the eye to notice. Nature reminds us that not every meaningful change must happen quickly. Some of the greatest transformations begin so quietly that they seem invisible at first. Only time reveals their true importance. And perhaps that is the deepest lesson hidden within the great ice ages. Patience creates landscapes. Small changes become extraordinary when given enough time. Curiosity allows us to understand what once seemed impossible. The more gently we observe the world, the more remarkable it becomes. So, as night grows a little quieter and this journey reaches its gentle close, Imagine the Earth continuing its endless voyage through the darkness of space. Above us, the stars remain calm. Below us, ancient rocks continue holding memories older than humanity itself. The oceans still breathe. The winds still travel across continents. And somewhere beneath the silent ice of Antarctica, tiny bubbles of ancient air continue waiting patiently, preserving stories from worlds long gone. Thank you for spending this quiet time exploring one of the greatest mysteries in Earth's history. May this ancient rhythm remind you that even the longest journeys begin with the smallest changes, and that the greatest stories are often written not in moments of noise, but in ages of quiet patience. Good night, and may your dreams drift as peacefully as the slow, timeless dance of our remarkable planet.